Okay.
So hello everyone and welcome to the Geoscience and Geoenergy webinar of the 21st of April 2022. So my name is Maartje Boon and I'm a colleague of Hadi here at TU Delft. And together with Sebastian Geiger, who is also from TU Delft, I have the pleasure to co-host today's webinar. And today is a bit of a special day since it's the 100th Geoscience and Geoenergy webinar. So we're delighted to host Ilenia Battiato from Stanford University as our distinguished speaker. So Ilenia Battiato received a master's in environmental engineering with the highest honors from Politecnico di Milano, Italy in 2005. And subsequently, she obtained a master's in engineering physics and a PhD in engineering science with specialization in computational sciences from University of California, San Diego in 2008 and 2010, respectively. She held a postdoctoral position at the Max Planck Institute for Dynamics and Self-Organization in Göttingen in Germany and was a visiting fellow at the Statistical and Applied Mathematical Sciences Institute in Research Triangle Park, North Carolina. In 2012, she joined the faculty at the Mechanical Engineering Department at Clemson University, and in 2014, she moved back to San Diego and joined the Department of Mechanical Engineering at San Diego State University. In 2015, she was awarded the DOE Young Investigator Award in Basic Energy Sciences for her work on multi-scale modeling of reactive transport in porous media. And in 2016, she joined the Department of Energy Resources Engineering at Stanford University, where she is currently assistant professor. So thank you, Ilenia, for graciously accepting our invitation. And to the audience, please note that this lecture will last for about 30 minutes, followed by questions. And please type your questions in the chat box, and then Sebastian will take them after the lecture. And please do not wait till the end of the lecture to post your questions, but just type them whenever you feel appropriate, as your questions may trigger other questions by other participants. So Ilenia, we're all very much looking forward to hearing your lecture. So please start whenever you're ready.
Well, first of all, thank you so much to the organizers for inviting me. It's a great honor to be here, and I really appreciate the opportunity to share some of the most recent work we have done in my group. This is probably like in the past year and a half. I would like to make a small disclaimer that to create context, I will have also to share some of more classical results. So bear with me if you have already seen some of the work. So today, as I mentioned before, I would like to talk about some of the recent work that we have done in the context of multi-scale modeling of reactive systems in porous media, but with reference to symbolic computing, and it will be clear in a little bit what I mean by that. So first of all, I would like to acknowledge the team. This was a relatively large research effort that was led by me here at Stanford, but it was in collaboration with PARC, Palo Alto Research Center, and a number of postdoc, PhD students, and research scientists were involved. However, the work that I'm going to present today is really the work of Kyle Petrick, who is my PhD student, fourth-year PhD student here at Stanford. So I'm sure I do not have convinced the audience that whenever we talk about modeling reactive transport in the subsurface, we are really dealing with a highly complex system for a number of reasons. And some of these reasons are outlined even in the title here. So we know that geologic media are fundamentally multi-scale and multi-physics systems. And these are just two sketches of what we mean by that. On the left, we have one of the sketches from our Center for Mechanistic Control of Unconventional Formations, and on the right, just an example of different scales that may be involved when we talk about, for example, CO2 injection. However, there is something else that adds quite a lot of complexity, and the fact is that generally these systems are highly reactive, and the reaction network involved are actually not simple reaction network. They can have a relatively high complexity, and this is just one example that I took from the literature, this is just a reaction network that is involved in hydraulic fracturing of unconventional oil and gas shales. But of course, if you think about CO2 sequestration of subsurface hydrogen storage, you can have reaction network of equivalent complexity. So really, when we talk about this type of systems, at least we have three axes of complexity to consider. First of all is the multi-scale axis, where we think about all the different length and temporal scales at which we may want to model the system of interest. The second axis is the multi-physics complexity. In these systems, generally, we have different types of physics that occur at the same time, and then it's the network complexity. Now, with the ever-changing energy landscape and the critical role that subsurface storage currently plays, and will play in the energy transition, then when I think about modeling, I start thinking about some of the needs that we may have to respond to this really ever-changing energy landscape. And one thing that comes to mind is fast development time. It's for people who have been working in developing models, I'm sure they are keenly aware of how complex these models are, and how long is the development time of this model from inception, which would mean generation and derivation of PDEs, to deployment. At the same time, we would like to have controlled accuracy across scales to some extent, computational efficiency, and also transferability and framework generality. When I talk about transferability, we would like to have frameworks that are both theoretical and computational, that whenever the new energy challenge comes about, then the infrastructure that we have built can be readily transferred to another field or another application. And so in terms of the state of the art, broadly speaking, when we talk about reactive networks in complex, multi-scale, multi-physics media, then there are generally two broad approaches. In computational physics, again, here we have the three axes of complexity: space, time, and network complexity. We are very aware that it's important to resolve the appropriate spatial and temporal scale, so we can generally build models that can include different scales in the same model. However, we tend to reduce the complexity of the reaction network if we are using, for example, upscaling methods that can be analytically challenging to deal with. And so, one example is to, build very complex multi-scale system, but where the reaction network complexity may be simplified. On the other hand, in combinatorial physics, they are able to deal with extremely large reaction networks, but they they take care of very well of temporal scales, different temporal scales. But the issue is that they generally neglect spatial complexity. And in fact, in combinatorial physics of large reaction networks, generally you would solve ordinary differential equations instead of PDEs. Now, we know that having a spatial resolution is very critical, because we know that reactivity is highly controlled by mixing at various scales. So our objective really in this project was to try to expand this type of capability to include spatial complexity, temporal complexity, but also not be limited in the network complexity. And so we have tools to do that in principle. And so we know that, when we talk about flow and transport in porous media, reactive transport in porous media, and I come from a fluid mechanics background. So for me, everything is at the continuum scale. It starts at the pore scale, but of course you can make arguments to go down the scales. So we can use pore scale models and use Stokes equation or an advection diffusion reaction equation if we are modeling reactive transport. At the continuum scale, if we want to model exactly the same physics, then we would use an upscaled representation, in particular, in this case, like Darcy's law or an advection reaction dispersion equations. And we are keenly aware of all the advantages and drawbacks. We know that pore scale models have that robustness, because predictive robustness, because they come from first principles, but of course they are associated with high computational burden just because of the hierarchy of scales that need to be resolved. On the other hand, continuum scale models have much lower computational burden, but they do rely on simplifications and assumptions, and therefore their robustness, may be in some sense case dependent on the dynamics and so on and so forth. I will discuss this in a second. And the connection between, and we have tools in porous media theory where we can rigorously derive continuum scale models from pore scale representations. And we know that there are a number of different methods. They're generally referred to as upscaling methods. In parentheses here, I'm just listing a few of them, but the list goes on and on. But these upscaling methods have been and continue to be really one of the cornerstones of subsurface hydrology because of different reasons. So first of all, they are used to derive Darcy scale models that can be both local and non-local, of different complexity. They can be actually used also to derive applicability conditions of the aforementioned models. In particular, these conditions are important to assess when these continuum scale models, at least from a theoretical level, can represent on average with prescribed accuracy pore scale processes. And this becomes important when really we are interested in some kind of predictive capabilities where we want some control on the error. And more recently, they have also been used to actually derive coupling conditions for multi-scale formulation. So the machinery to transfer information, regardless of the complexity, from pore scale to the continuum scale exists. And so everything is excellent in theory. The good news is that, again, here I restrict myself to advective diffusive reactive systems, but we can talk about also multi-phase flow and other types of physics. So the good news is that the rigorous upscaling methods have enabled the systematic generation of macroscopic differential equations that can accurately account for microscopic phenomena. And the enticing aspect of these approaches is the possibility, again, at least theoretically, to construct multi-scale models that can seamlessly connect adjacent scales. And this means that no parameter fitting at coarser scale is required if the appropriate information at the finer scale is known. So everything is good on paper. However, in practice, there are some bad news. So we know that the mathematical derivation of advection diffusion reactive equations at the continuum scale is actually a pretty long endeavor. It's tedious, time-consuming, prone to error. It involves a lot of mathematical technicalities, even for syntactically simple advection diffusion reactive systems. Now, when I talk about syntactically simple, I talk about reactive systems of the type A plus B goes to C. So very, very simple, completely idealistic scenarios. And on top of that, if we want to obtain a priori guarantees and sufficient conditions under which these equations are valid, this can actually take further, effort for additional derivations. And so the entire process, we can understand easily, that becomes quickly intractable for complex systems where you have actually hundreds of, tens or hundreds of species or equations, multi-physics, multi-scale, very complex reaction network. Now, the issue is that we have this nice, very elegant tool and very useful tool, but practically, as of now, has been primarily restricted to very idealized systems. And the question is there a way that we can actually democratize the use of this type of techniques so that they can be more broadly used in realistic applications, in realistic systems where complexity is not a tuning parameter? We cannot have that. We don't have that luxury of reducing complexity. And so as a modeler, I'm keenly aware that routinely we have to simplify systems. And in general, there is this spherical cow approximation I'm sure everybody is aware of. The argument is that neglecting higher order effects, it's reasonable to assume that the spherical cow approximation actually works. But this is also true when we talk about porous media modelers. In particular, we always like to think that neglecting higher order effects, it's reasonable to assume that the spherical grain approximation actually works and that we have very simplified system, despite reality is much more complex. And so again, we know that in reality, we have multiple spatial scale, very complex reaction network. The question is, can we use this type of tools to get to study systems like this in a rigorous way? Now, here is where I have to provide a little bit of background information. So my apologies if you have seen some of this. The goal to respond to this for us was to automate. It was clear to us that the human component of this process was probably one of the main limiting factors. And so our hope in this project was to be able to essentially automate the physics-based model development, where we would use recursively these upscaling methods to derive equations at different scales. And so we still do learn a lot from the spherical cow, and this again provides context for what I'm going to say later. And so what do we learn from the spherical cow in the context of porous media is can be outlined in this example. So what we see here is a very classical problem of transport, reactive flow and reactive transport in a canonical porous medium, in a canonical pore. So this is just essentially flow in a channel with reactive walls. And so at the pore scale, we have an advection diffusion equation, and then we have the reactive wall. So we have, proper boundary conditions at this bottom and top interface. And if we want to construct an upscaled representation, then we have to define an average. In this case, the average is intuitive, would be the average along the vertical cross section. So now if you apply this averaging operator to this equation, then after many pages of technical mathematical derivations that can be found in this remarkable piece of work by Michelic, then you would obtain this continuum scale equation. So this is like the classical advection reaction dispersion equation. But what I would like to point your attention to is this effective reaction rate. So we know that the effective reaction rate at the continuum scale clearly is related to the pore scale reaction rate, which is this K over here, the curly K, and then this Damköhler number. Now, this Damköhler number is a ratio between diffusive timescale and reactive timescale. So if diffusion time is fast, which means that diffusion acts on a very fast timescale, then Damköhler number is small. Now, let's make just an example. For example, a situation in which we increase this reactivity of the wall progressively. So if we increase K, we don't change the physics, we just increase K, then Damköhler number increases. But then what we see is that when Damköhler becomes larger than 3, this effective reaction rate changes sign, which of course is unphysical, because we are not changing the underlying physics, we are just changing the time scale over which reactions occur relative to diffusion. And so this example, which is incredibly insightful, demonstrate that essentially these continuum scale equations always come with attached applicability conditions that can be formulated in terms of these dimensionless numbers, orders of magnitude of dimensionless numbers. And the importance of having this pairing always come about is that, again, we want to preserve predictivity and have control over the error, over the upscaling error. Now, of course, you can use this similar example to look at more complex systems that can still be done by hand. And so you can do the same in this particular case. For example, if you have the, again, classical A plus B goes to C, and then it precipitates and becomes S, you can identify 4 dimensionless numbers. And then in this particular case, you would have to write pore scale equations for the 3 species A, B, and C, boundary conditions. And then we applied multiple scale expansion, which is the technique that we are going to focus on today. And multiple scale expansion is based on the representation of concentration in terms of different spatial and temporal scale, and asymptotic expansion in terms of a separation of scale parameter, and then other mathematical derivations to lead to your continuum scale equation. So these are very classical advection reaction dispersion equation, where your effective dispersion coefficient, d star, can be written in terms of this closure variable that itself, my office light goes off after some time. This dispersion coefficient can be written in terms of this closure variable, and the closure variable essentially satisfies a boundary value problem on a unit cell. Now, this boundary value problem can be completely decoupled from the continuum scale problem only under certain conditions, similarly to what we have seen before, that can be written in terms of these orders of magnitude of dimensionless numbers. So if you are within this region, then your upscaled equation is a good approximation of four-scale processes. But if you are outside, your the accuracy of your model is not guaranteed. I think the bottom line of this even very simple example is that even just for a system of A plus B goes to C, you already have 7 dimensionless number. And in this plot, I'm just looking at 3 of them. So these constraints can become incredibly difficult to derive when you start having systems that are like of a larger reaction network that are of a larger size. So you have these constraints on the physics. So the question is, okay, so how do we use these techniques if we really want to bring the rigor to systems with realistic complexity? And I know we are all aware that, of course, data-driven methods have been looked at and are being looked at, and are incredibly useful in a number of different applications. Including derivation or learning of PDEs. However, there are some intrinsic drawback just because of their data-driven nature. So first of all, they lack error estimates. They have generally issues of extrapolation. So if you try to extrapolate to different conditions, things may not go as well as you expected or you hoped. And then there is a problem with transferability. So because of there are data-driven processes, then of course they have to be trained, but the moment you train, it means that you are specializing that model capacity or capability to that specific training set. So you reduce transferability. And so in the context of mathematical modeling, where we are very used to think about numerical computing and data-driven method, we started actually thinking towards an axis that was maybe not so explored in the context of transport in porous media, which is symbolic computing. And so symbolic computing clearly is not anything new. In particular, it was the first idea of symbolic computation was brought by the Countess of Lovelace, Ada Augusta, in 1842. And so she actually I think in a very beautiful piece of notes, she wrote that many persons who are not conversant with mathematical studies imagine that because the business of the Babbage analytical engine is to give its results in numerical notation, the nature of its processes must consequently be arithmetical and numerical rather than algebraical and analytical. This is an error. The engine can arrange and combine its numerical quantities exactly as if they were letters or any other symbols. And in fact, it might bring out its results in algebraic notations where provisions made accordingly. So this was really the first concept that led then to the development of symbolic computation. And we know about symbolic computing because of Mathematica and other tools. Essentially, symbolic computation emphasizes discrete and exact computation where symbols represent mathematical objects subject to predefined rules. However, although symbolic computing is routinely used in certain branches of applied and theoretical mathematics, for example, combinatorics and computer science, formalisms, such as those involved in high-level manipulations of mathematical constructs that are involved in upscaling method, has never been implemented before. In the context of generally Mathematica and these kind of tools are more generally used as symbolic calculators. And so our objective here was to try to actually start using or developing codes where we don't use these tools as calculators, as symbolic calculators, but as symbolic computers. So we wanted to add a level of conceptual and algorithmic complexity to see if we could recursively implement whatever a human does when it has to go through, for example, upscaling techniques. Okay, so and so what we did in this work was really to combine, to develop an homogenization framework in the context of symbolic computing. And I would like to note that we used homogenization theory just because we routinely use this approach. Is just, I would say, a matter of taste. But I think the take-home message is that with this particular result that I'm going to discuss, we demonstrate that this type of complex methodologies can be implemented symbolically. And so I would assume that you would not have limitations to implement symbolically other types of upscaling, be it volume averaging, thermodynamically constrained averaging, and any stochastic homogenization, and all these kind of things. So although the upscaling of few equations can be handled by hand, real systems, as I mentioned before, may include hundreds of species and reactions. They have different physics. You may end up with a large system of PDEs. And automating the upscaling procedure then becomes critical to develop upscaled models in the engineering applications where you want a priori error guarantees and you want to inject more rigor in your upscaled models. And so what we did was to employ symbolic computations to automate the homogenization procedure. In this particular talk, I'm going to discuss just a couple advection diffusion reaction systems, but we have done it for essentially almost arbitrary PDEs. And so what we did was to develop Symbolica. So this is a symbolic software that is developed in Mathematica, which automates the upscaling procedure by multiple scale expansion. And now the nice thing is that by automating this upscaling procedure and allocating all these cumbersome symbolic manipulations to computational resources, large multi-scale systems that are common in engineering applications become more practical to model. And so this Symbolica actually is part of a workflow to provide an automated turnkey solution to model multi-scale reactive transport. So although Symbolica represents the upscaling component, this is actually part of an entire workflow where we can automatically parse PDs at the pore scale from just a very few structure of the reaction network and the common chemical libraries, and then these are parsed by the computer, then are fed into Symbolica. Symbolica upscales them, provides applicability conditions, and then these are fed into a numerical simulator. And so really the objective here was to cut down the development cost of multi-scale models. And so now I'm going to go in some of the details of the code. So essentially what Symbolica does is that it takes in equations at the pore scale and boundary conditions. So in this particular case, it could be a system of arbitrary size of advection reaction diffusion equation and boundary conditions on all boundaries that you have. So then essentially once you feed these PDEs into Symbolica, Symbolica performs the symbolic upscaling by multiple scale expansion and provides upscaled equations for ranges of dimensionless numbers that are prescribed by the user. So this is just an example. So you provide the inputs, so you have the PDEs, you have the boundary conditions at the pore scale, and you have to provide scales, and forms of the dimensionless numbers. Then once you provide this information, Symbolica actually non-dimensionalizes the PDEs, so it finds the dimensionless numbers inside the PDEs, and then what it does is that it essentially iterative. So in this particular case, we have three dimensionless numbers. So we have triplets of Peclet, Damkoller 1 and Damkoller 2, and then what it does is that it provides upscaled equations for different tuples of these dimensionless numbers. So in that phase diagram that I showed you before, essentially what Symbolica does is that it performs the upscaling n times at each point in this n-dimensional phase space, and for each point in this n-dimensional phase space provide the corresponding upscaled equations. As an output, it provides the upscaled equation, provides the definition of all the effective parameters, provide the definitions of all the closure problems that then can be fed into a numerical simulator and solved numerically. So this is just the structure of Symbolica. We have a preparation phase, an upscaling phase, and then an upscaling routine. And now this is just an example of an output. It doesn't look pretty, but conceptually, I think it's helpful. So as I mentioned before, Symbolica spans the phase space, the n-dimensional phase space that is identified by all the dimensionless numbers that Symbolica finds by direct sampling, and provides upscaled equation, closure problem, effective parameters for each tuple of dimensionless numbers. So for each permutation that that the user specifies in terms of that range of parameters. So for example, for just 3 species, and this completely idealistic reaction, A goes to B and it's reversible, and then H produces A. If we specify so we have, for these 3 species, 7 dimensionless numbers, already 7 dimensionless numbers. So we would have to span a 7D phase space. If we want to, for example, investigate ranges of these dimensionless numbers that range from -1 to 1, from 10 to the -1 to 10, with integers increasing, going from from 10 to the -1, 0, and 10, then what would happen is that we would have 81 points in this 7-dimensional space. So these are all the permutation that Symbolica will upscale the system for, and then it provides essentially 81 system of PDEs. So the thing goes on and on and on. If I focus now on one of these points exclusively, what we see is that these are just the 3 upscaled equations. This is the upscaled equation for the concentration of the first species, for the second species, and third species. And what we see here is essentially the effective dispersion coefficient that is written in terms of this closure variable, chi, and the effective velocity. It also provides as outputs closure problems and closure boundary conditions. Now, the question is, okay, we get from this symbolic software, we get out a PDE or a system of PDEs. How do we know these are correct? The nice thing is that this can actually be verified. So what we do is that we input the reaction network, we get the PDEs at the pore scale, then we solve the PDEs numerically at the pore scale, and then we average them in space. So this is considered the exact averaged microscale solution. In parallel, we feed these PDEs with these pore scale PDEs to Symbolica. Symbolica produces the macroscopic PDEs. We solve them numerically, and this is the approximate solution. Then we compare these 2 solutions, and if Symbolica provided the correct upscale solution, then we expect that the absolute error at any time, at any location in space, should always be bounded by epsilon in this particular case, because we look at first order at errors of order epsilon. And so if the absolute error between these 2 solutions is lower than epsilon, then the upscaled equation provided by Symbolica is actually validated. What we did was to go back to actually the classical cases that I had solved as a PhD student and sweat over them for like many, many months. And so what we did, like the first case that we validated, was to look at the nonlinear heterogeneous reaction case. So we have just an advection diffusion equation, and this the very classical heterogeneous reaction. And so here we have the phase diagram that I had derived in terms of Dunn-Kohler and Peclet number. And this boundary, it's what I had found based on the need of introducing parametrization to be able to upscale many cases at the same time in one shot. What Symbolica found was, in fact, that the applicability conditions that I found were actually unnecessarily restrictive. So actually, reality was a little bit more forgiving than what we had calculated, because in the process of doing this, we had to include restrictive hypotheses to be able to just handle the math. But the most striking thing was that essentially what I did in 1 year as a PhD student, Symbolica did in 14 seconds. So that was quite depressing, but we continued and we looked at another case where we had A plus B goes to C. This is also a case that we did by hand. And again, what Symbolica found by direct sampling of this phase space was again that the applicability conditions that we found were overly cautious. And then we moved to another case where we looked actually at 10 species. So this is a case that we absolutely couldn't do by hand. In particular, this is just a fictitious reaction network. I would like to emphasize with 10 species, I believe you have 22 dimensionless numbers that you have to look, and this phase space becomes just intractable. And so what we did was numerical validation for 2 cases, reaction controlled and advection controlled scenario. And here we have again the solution for the concentration for the concentration of these 10 species, both from the continuum scale obtained by Symbolica and the accurate solution. And what we see is that the errors are always bounded by epsilon as expected by the upscaling theory. This is also true for the advection controlled case. Now, this is just a summary of performance. So for the first problem where we had the classical single species heterogeneous case, Symbolica sampled 36 combinations in this 2-dimensional phase space and could obtain for all these combinations the upscaled equations in only 13 seconds. If we go to the 3-species case, it sampled 625 combinations in a 7-dimensional phase space, and it did so in a little bit over 8 minutes. And if we looked at the case for 10 equations, so for a 22-dimensional phase space, for 2 sample combination, it took 64 seconds. So the last thing that I would like to emphasize is that most of the execution time, as you can see from this breakup, here is that this is really dedicated to the upscaling phase. But the upscaling phase can actually be easily parallelized due to the independence of the upscaling procedure at each sampling point. So this can be immediately parallelized, and essentially these numbers would suggest that essentially to upscale one instance in the phase space takes in the order like of few seconds. And of course, this is what we are expecting to get. So I'm going to conclude. So the current capabilities, we actually have capabilities to deal with heat transfer type of problems with nonlinear source terms in domains with heterogeneous inclusions. We also have implemented additional capabilities where now we can generalize the closure forms and essentially expand the applicability conditions. In particular, what I'm not showing here because I don't have time is the fact that when you start expanding and pushing the boundaries of these applicability conditions, you can really observe upscaled equations that completely deviate from anything that is intuitive. And I think this is, where the largest promise is. We will leave behind our biases of what an upscaled equation should look like. We have included also derivation of higher order terms that, of course, when you do things by hand is very complex because you need to keep, adding terms to this expansion. Now we can provide models with error of the order epsilon square, and we can do multi-domain unit cells, which we hope to use for multi-phase flow. This is just an example of higher order terms where we can just include a loop and we can get upscaled equations to order epsilon square, which do not look anything like what we would expect. Future developments, we want to implement time averaging procedures. We want to implement upscaling of vector fields because we would like to generalize, for example, to the Navier-Stokes equations and maybe expand into multi-phase flow. And then we would like to start embedding Symbolica into optimization framework. And of course, with this, I think we demonstrated that there are potentially a lot of very highly sophisticated analytical methods that are used in physics, in applied physics or applied mathematics that could be actually optimized. The generation again of PDF equations and any other type of upscaling techniques and so on and so forth. So with this, I would like to acknowledge DARPA, who actually funded this project, and I thank you very much for your attention, and I'm ready to take any questions.
Yeah, thank you very much, Ilenia, for this very nice and very interesting presentation. There are several questions already coming in, so Sebastian, please go ahead.
Yes, thank you very much from me as well, Ilenia, for a great talk. And if you just unshare your presentation, I think then you can start seeing us.
Is this good?
Again, that's perfect. Yes, yeah. So yes, thank you again for your presentation. We do have a number of questions that came through, and I'm going to start with the one from Sarah. She says, thanks for the talk. I'm interested to learn what are the most important challenges when using symbolic computing and upscaling methods.
Yes, so I kind of completely not even discuss this. So it's like I try to make the pill as not bitter as possible. But really, I think the challenge on the technical point of view is to develop computer algebra algorithms that allow you to do in the computer what your brain does, right? So how do you define that the left-hand side of something is equal to the right-hand side of something? How do you collect terms, right? We have all this kind of knowledge as modelers built in out of experience. And so the hardest part was really to code in recursive structures, recursive symbolic structures that then would essentially be able to traverse these very complex trees, logical trees, to make the computer do what you would do by hand almost instinctively. And so I think that actually there is a lot that can be done in the computer algebra field to allow the development and implementation of much higher order, higher complexity conceptual structures. And so I think that's the technical challenge is there, like is how, what are the computer algebra algorithms that you have to develop to make sure that this is equal to that. The computer recognizes what a dimensionless number is. How does it find a dimensionless numbers? How do you define it? You want to automate most of it because you want to reduce the interaction with the user so that very few people have to learn these techniques. And so if they don't have to learn it, then maybe there is a chance that they will be more prone to use them in their application. So yeah, the mechanics of it, that's the challenging part.
Okay, it's really interesting. I haven't thought of making a computer think and recognize the pattern that we see, and that's a.
And there is no AI here, right?
Yeah.
So just recursive. It's like you do things recursively, and if you do it right, it will do the right thing. So there is no learning. It's coded, there is no learning.
And you mentioned dimensionless numbers that the computer needs to recognize, and sneaking in one of my questions here. So are you predefining the dimensionless numbers, or do you let the computer identify them? Because dimensionless numbers also often have some physical meaning. So how do you?
So yes and no, in the sense that the only thing that the user has to do is to define, and this actually even that can be automated. We just didn't have time to do it. You can actually construct libraries of this, and then so essentially you have to define dimensionless numbers forms. Like, for example, anything that looks like a length scale multiplied by a velocity scale divided by diffusion, I call it Peclet, right? So this can be, parsed previously, right? So you can have a library of the most, common dimensionless numbers, and then the computer will use the scales that you introduce and actually, go through all these dimensionless numbers. And when it finds a form that it recognizes, it introduces it in your equations, right? So you have both options. You can no, they're not predefined. You can have like a list of, dimensionless numbers forms that are not your dimensionless numbers. The computer finds them, but it's the form, like length multiplied by velocity divided by diffusivity, right? And then if the computer does not find that specific form, it just doesn't give it that name. It just gives like a default name.
Yeah.
So you can find a new dimensionless number, but you can still identify classical dimensionless numbers if you're willing to, provide. We wanted to do this, like provide the library so that it's all automated, and then, everybody can build on that library so that, if you do thermophysics, you have your dimensionless number. If you do fluid mechanics, you have other dimensionless number. If you do whatever, plasma physics, you have more things, right? But yeah, it finds it. It finds it.
Okay, thank you much. So Soren Popp has a really nice question. I think it's a slightly longer question. I'm trying to read this step by step. So he starts out says, "Thank you very much, Ilenia, for the nice presentation. Many steps in homogenization can be automated. So I think it's excellent to have a symbolic tool to carry them." And I says, however, that's the nice part. However,
that's the sandwich. That's the sandwich.
Yeah, that's a sandwich. Yeah. Don't we need to know a priori the form of the upscaled equation? Isn't that first one has to derive the upscaled model, and then let the symbolic tool determine the effective parameters? And here's a follow-up question.
That's the beauty of it. No, and that's the part. Unfortunately, I did not include here some of the most awkward upscaled equations that we found, both because we're working on them right now, but also because the others one that are more established, actually they apply to thermal runaway in battery packs. Okay, so it wasn't really pertinent maybe to this topic, but no, that's the beauty of it. In the context of battery packs, right, what we did was to start with a standard, super boring conduction equation. So we assume that, we have a battery pack. It has two materials. So it's a packing material with inclusions, which are the batteries. So you have essentially two conductions equations. Like classical PD is nothing strange. You only have one nonlinear term that represents, how heat is generated because of chemistry, whatever. So if you, like as a human, if I were to upscale, I agree with you, tend to think that I'm going to get an upscaled equation that looks like a conduction equation. Well, when Symbolic upscaled it in certain regimes, what we found was the appearance of an advective term that coupled everything. Super strange, weird. But what that term did was actually to be able to model explosions. So you can start, so it's like the thermal runaway problem, right? So you essentially, the battery catches on fire. And so what you see in the continuum scale equation is that you start very nicely with a, conduction problem, very boring diffusive behavior. And all of a sudden, bam, you generate a thermal front because this thing ignites. So no, we don't have to hypothesize anything. And that's, I think, the beauty of it, because sometimes we implicitly, as modelers and people who do upscaling, we kind of project a lot in what we want to see in the upscaled equation, but the computer is agnostic in that sense. And it just does what it has to do. And you do get equations that you would never expect. And it actually is taking us a lot of time to understand what these things mean physically. We are writing now a paper because we're trying to figure it out. But yeah. Some of, for the battery case, we understood what it was. It was literally thermal runaway and the thermal front propagating. It was ignition. In some reactive problems in transport in porous media, we find things when we start including higher orders that we currently do not understand. But they are correct numerically. So we can, upscale the, we numerically solve the pore scale problem. We solve the continuum scale problem. They are the same up to order epsilon or epsilon square. So we do not have to postulate. I think that's the beauty of it.
So your answer is a really nice segue into Christine's question, who also says, thank you for the interesting talk. How well behaved is the system of the upscale PDs after upscaling? Because you said you get terms that you didn't quite expect that they're there and you struggle to understand them. Have you encountered convergence issues when solving them on the coarser scale, or is everything really nicely behaved?
No, it's you just get whatever, some kind of weird equation, and then you have to use whatever appropriate numerical scheme to solve it, right? Depending on what type of equation it is. No we didn't have, the problem was never on the numerical side or implementation side. It was more like, what the heck is this? But then we understood it, so that's
Soren has a comment, says, exciting, congratulations again. I really want to learn more about it. And again, he comes with a question, says, when saying that if the Damkohler number is too large, homogenization will not work, isn't it rather that the upscaled model is different from the one for small enough Damkohler numbers?
It's both, right? In the sense that beyond and again, so these are like super interesting questions, right? Because the best the best example I can make, it's when you go on an exploratory mission and you stop somewhere, right? And then you look back and you say, okay, this is what I know up to now, but I cannot know beyond this point. And so to get back to Soren's question, so it's both, right? So for sure, we know that, depending on the Damkohler number, the magnitude of the Damkohler number, the upscaled equation will change, okay? However, I also believe that there is actually a limit up to what upscaling can do. So I do believe that beyond a certain Damkohler number, regardless how different your upscaled equation is, you actually gotta stop. Eventually, you cannot decouple scales anymore. So it's both, right? I think there is a hard limit, but again, this hard limit, it's like the boundary where, like the exploratory mission. As of now, I believe that there is a hard limit. Now, will I find tomorrow a better closure problem that will allow me to trick out that limit and maybe, still separate scale one piece more? Maybe. I think at one point there will be a hard limit. And I respond to it just intuitively by saying that, we need some kind of mixing at the pore scale if we want to decouple scales. So sooner or later, if you have this reaction that is very, very strong, eventually your concept of average will mean very little. And so that's why I think that there will be a limit. I cannot tell you for sure where that limit is. I can tell you up to what point we could push it. And I think it's Damkohler of order, I forgot. We found something recently, I forgot. But yeah. But it's true that you also have different upscaled equations before the limit, before you reach that hard boundary.
So time is slowly coming to an end, but I have one question myself. What is the limit of the approach? So how far can you push this in terms of the physics? So I think from the examples, for example, that you showed, if I saw this correctly, you assume that the velocity field is stationary and doesn't change. There's no feedback between the reactions and pore space being occupied or some dissolution. So how difficult would it be, for example, to use with a non-stationary transient velocity field, so when porosity changes or two-phase flow processes?
I mean, yeah, this is like, there is a world out, right? It's a universe, right? So I think that anything that we as humans have done in this upscaling for all these very complex cases can be done symbolically. It will be, complicated because, and that's why, we have to, we want to implement this for vectorial fields, right? Because we want to be able to work with the Navier-Stokes equations and multi-phase flow, and, and then of course you can add the dynamic of the interface, and then you can also add moving boundaries, I know, for example, that homogenization procedure has been used in the context, successfully used in the concept of moving boundaries. I am not, too strong on that, specific application. So I'm not much aware of, what are the technicalities of it. But I think that anything that we have done so far, by hand, can be automated. I think that then how far I think it can go as far as homogenization does, right? And maybe, yeah, it can go as far as that, right? There will be problems that cannot be upscaled. We know that, right? But in that case, Symbolica will just tell you, bad luck. You gotta do, you have to couple scales, and that's or you have to do non-local problems, right? In that case, I think also that can be automated, maybe different techniques, right? So I think it can be really far, can go really far.
I just see there's one final question has come in, and sort of again, sort of the range of applicability. And I just give you the opportunity to comment on this very quickly. From Alex, says, thank you for a nice talk. Your approach seems very general. I believe a big amount of work about upscaling was done in quantum statistical physics. Can it be applied already? Has it been applied to that field?
Well, I don't know. Look, I've not heard of this type of techniques ever being automated, right? But this is to the best of my knowledge. So I don't believe so. And I think, yes, it can be applied. I think it's as broad as numerical methods. Like in terms of, like, if we start looking at, numerical computations and the fact that there is finite volume, finite difference, and, finite elements, and this and this and this, I think that symbolic computing in the context of applied math has that same potential. It's enormous and across every discipline. I would not see why not for statistical physics. Yeah.
Well, Ilenia, thank you very, very much again for a great talk. And I think also a very fitting talk. Today is the 100th webinar that we have. It's a forward-looking talk about all the new tools that we can do. I always think, as academics, one of the greatest things is if you find out later on how you could have done your PhD. I was in the same situation.
5 seconds.
In a few weeks rather than several really, really hard years. So for all the PhD students listening, you're not alone. We've been through that pain ourselves. So it's a wonderful message. So thank you again, Ilenia. Thank you for the audience for great talks. Marcia, over to you for some closing remarks.
Yeah, so thanks a lot, Ilenia. It was really, really interesting. So I'd like to take the chance to introduce our next week's speaker. So next week we will host Ronnie Pini from Imperial College, who will speak about chemical transport in disordered porous media. So until next week, and as Hadi says, stay happy, healthy, and tuned into our Geoscience and Geoenergy channel. So see you next time. Thank you.
Thank you, everyone. Thank you. Bye-bye.
Bye.